Aubrey de Grey is one of the most prominent figures in longevity and aging research. He believes that humans can live for thousands of years, and he's working really hard to make it happen. But very few people know of his mathematical research. In 2018, he made a breakthrough in Hadwiger Nelson problem, which asks for the chromatic number of a plane. It was the first serious improvement to this problem in over 50 years. There was so much to learn from him, and I hope you enjoy our discussion as well. So most people will recognize you as a leading researcher into the problems of aging, longevity, but you are also, as one may describe, an amateur professional mathematician because you made a breakthrough in something called Hadwiger Nelson problem about 4 years ago, and you actually started your career as a computer scientist. So what subject is primary to you, and who are you?
Sure. Okay. Great way of asking the question. Definitely, for sure, my biology work on the biology of aging is primary to me. I do maths as pure recreation, just for fun. I guess my background in computer science before I became a biologist has been helpful to me in my biology work and also in my recreational work. Before I was a biologist, I had a bunch of friends at Cambridge who were mathematicians and who introduced me to combinatorics, in particular, graph theory. And it turned out that I was very good at it. I succeeded in solving problems that most mathematics undergrads would not have been able to solve. So ever since then, I've kind of enjoyed doing it for recreation. But the way I treat it is very much that I'm interested in simply studying problems sufficiently so that I get a rudimentary understanding of why they are hard. I never had any expectation at all of actually making any progress, any actual breakthrough.
If we look at your sort of biography, we can see that you're a chief science officer at SENS Research Foundation, that is SENS, which does research into age-related diseases. But it seems like you do not belong to any particular institution or a public group of researchers, at least when it comes to mathematics. So you appear as an individual researcher. Did you choose that lifestyle on purpose, and how do you find it productive? How do you make it productive?
I did choose it on purpose. I think that in most areas of endeavor, certainly in academia, there are big problems in working within an institution and having a boss and so on. And I got lucky at various times in my life in being able to avoid that and being able to basically, achieve what I wanted to achieve without having to do what somebody told me. So yeah, it seemed to suit me.
At this point, it seems reasonable to mention that you got your doctorate in biology without actually being registered for graduate study. Is that correct?
That's correct, yes. It's a relatively rare thing, but it's been an established method of getting a doctorate at Cambridge and I think also at Oxford for many years. Essentially, it's designed for people like me who switch fields or who, for whatever other reason, have not done a doctorate in their original field in the normal way. So Wittgenstein got his PhD that way for the Tractatus.
Yeah.
And there are a few other examples, reasonably well-known ones. But yes, so I started publishing in this area. I wrote a paper that was well received, and somebody asked me to write a book expanding on it and incorporating subsequent work, which basically included, in the end, my first half dozen papers, really. That came out in 1999. And just towards the end, as I was just finalizing it, I was told about a system where you could get a doctorate for published work even if you had not been registered for as a PhD student, just so long as you did your undergraduate work at Cambridge, which of course I had.
Do you think it's something specific for Oxbridge institutions? In other words, can people nowadays repeat the same trick around the world, or would you not recommend risking 4 years of your life for such an endeavor?
I would certainly recommend it to anyone who has the opportunity. I mean, it saved me a lot of time. You know, it's quite useful having those letters up to your name, just in terms of, you know, the first impression, making sure that people pay attention to what you say. And I didn't have to spend any time. I just got this degree for what I'd already done. So I definitely recommend it. How available it is? Well, all I know is that in the 20 or more years since I did it, I have not actually been told of any other university outside of Cambridge, not even Oxford actually, though I think it must be available at Oxford, that does this thing.
I mean, people do it in the States all the time. If you read,
not exactly, no. So in the States and in Europe, certainly people very often get their doctorate on basically their thesis consists of a compilation of papers that they have published and not much else, right? Which is kind of the same thing, but they only get it if they were actually registered to be a PhD student for a respectable amount of time.
Right. So just to conclude on that part, what mindset do you need to have in order to make tractable progress for all those years, as you say, at least 3 or 4 years, and just not lose track of whether you are still into it or you rather do something else, because you're not really part of that community on an official basis. So how do you find that orientation inside you?
I don't think it's all that at that level. When one is a PhD student or one is learning how to do research, I don't think there's all that much difference between doing it within mainstream academia in a normal way versus doing it outside of academia the way I did. I think really, the main thing you need is extraordinary determination and ability to withstand the long periods of frustration where nothing is working, right? So when I graduated from Cambridge in my undergrad degree in '85, after that I spent maybe 6 years doing research in artificial intelligence research, specifically in the area of software verification. And I was doing this on my own. I basically ended up in this crazy situation where somebody was paying my bills, but I wasn't affiliated with Cambridge or any other university. I was basically just doing that kind of surrogate PhD in my bedroom without a supervisor. And, it was pretty much the same as if I had had a supervisor, really, even if I had less communication with other people in the field. But communication is not the number one thing. It's important, but it's not the number one thing. Determination is the number one thing. So, in a sense, I guess, in those 5 or 6 years, I got lucky in the sense that I didn't give up. I was like, I didn't have any really long periods of frustration. I was making relatively steady progress throughout that time. So, I was, progressively gaining in confidence that in specific terms I was making progress on the problem I was working on, and also in general terms that I was good at working on really hard problems. So, that stood me in very good stead, and it was a big part of why I felt that when I understood that the biology of aging wasn't moving as fast as it should, that I might be able to make a contribution, despite not having any formal training beyond the age of 15 in biology.
Sure. Well, your doctorate thesis is actually a book, and it's a book about mitochondria. Why did you dedicate your kind of thesis to that particular organelle? And do you feel like your deeper understanding of this particular part of a cell is helping you in sort of defining and progressing in problems related to aging?
So honestly, it was just a starting point.
Okay.
Aging is an extraordinarily complex, it's not even a process, it's a collection of processes that happen in relative synchrony, but really it's just a chaotic bunch of different things happening at the same time.
Mm-hmm.
And the accumulation of mutant mitochondria is just one of those things. It just so happened that because of the random walk that I had into the literature, as I started to decide to get interested in this, that was the area that I gravitated to first. And it was the area where I published first, and I had, well-received ideas first. But even by as early as 1998, certainly 99, I was beginning to think that, I really needed to look beyond that more generally. I was obviously going to meet conferences on biology of aging and learning about a whole bunch of other things. And I was beginning to see that one could not even begin to believe that there was one single dominant process within aging. It was clearly a multiplicity of processes. So it was really, during about 99, first half of 2000, that I began to crystallize that, and that's how that led me to this kind of big eureka moment that has led to everything else that's gone on since then. In the summer of 2000, where I realized not only that aging is this hodgepodge of many different processes of damage accumulation, but also the way to address it medically is not to slow down the rate at which the body generates this damage, but rather to repair the damage afterwards when it's already happened, but before it has reached a level that makes you sick.
For anyone interested, I just want to reference your book called Ending Aging, where you effectively outline your vision and actually your kind of step-by-step program on how we can fight those problems and achieve either immortality or at least a substantial increase to our lifetimes. But if we shift our focus to mathematics for now, let me remind
let me make sure that the audience understands that that's a separate book from the one we've been talking about before, the one that I got my doctorate for.
Exactly, so, that's the doctorate, and this one came later in 2007, I believe.
That's exactly right.
Sure. So yeah, if we talk about Hadwiger Nelson in particular, just to remind the audience, we have a two-dimensional Euclidean plane. We use different colors to cover it fully, and then we take points that are unit distance apart, and we want those points to belong to regions of different color for any such pair, and we want to do it with the least amount of colors as possible, and this is called the chromatic number of a plane. People who do graph theory might know this from chromatic number of a graph, where the problem is essentially the same, but you talk about vertices instead of all points on a plane. Now, the lower bound of 4 colors and the upper bound of 7 colors was proved back in the 60s in a rather trivial way. People can remember the Moser spindle and the hexagonal cover of a plane for those upper and lower bounds. And essentially no progress was done to establish the exact chromatic number of a plane ever since, up until your work came up, where you demonstrated that the lower bound is actually 5.
Okay, so to correct some small details of what you said. So the problem was first posed in 1950 by Ed Nelson. So Ed Nelson was at that point an undergraduate. And John Isbell, who identified the hexagonal coloring, the honeycomb coloring that gives the upper bound of 7, was also a friend of his, actually, also an undergraduate. Mm-hmm. So, as with many things in mathematics, when somebody has never just even thought of asking questions in a particular area, the first steps are really easy. So, basically this idea of the lower bound being 4 and the upper bound being 7, that came instantly. And it wasn't very long before Erdos came along with de Grey and noticed that the lower bound question could be converted it into a question about finite graphs. In other words, that the plane can be colored with k colors if and only if there exists a finite graph that needs k colors, and there exists no finite graph that needs k plus 1 colors. In which it's embedded in the plane, of course, so that every edge of the graph is exactly unit distance long. And so that's where the Merger spindle comes from. It's a 4 chromatic graph, 7 vertices. It was discovered in the late 50s, I think. And as you say, that was basically, there was no progress between then and when I realized how to do it.
So you mentioned this in the beginning, but what was your motivation for even beginning to consider this open question, essentially? What gave you confidence that the time you will put into thinking about this problem might lead you somewhere in a productive direction?
So I really did not and do not think in terms of feeling that I'll work on some, in order to get my motivation from some expectation of making progress. That's not why I do these things. Mm-hmm. I do it purely for fun. I'm interested in finding out why a problem is hard, really. And if I find that out, then I'm happy to give up on it, right? So this was a complete accident that I actually did make progress in this occasion. So why this particular problem? Well, okay, the first question I actually want to address is why it took me so long to come across this problem.
Right.
Because I mentioned earlier, I had masses of friends back from the 1980s who were in combinatorics and graph theory, and through whom I had heard about various other problems. I'd never heard about this one for whatever reason. Mm-hmm. And I suddenly kind of came across it in 2018. I actually can't completely reconstruct how I came across it. But a huge part of how I got interested in it and decided I was inspired to actually spend a bit of time on it, was that I stumbled across this amazing book called the Mathematical Coloring Book by Alexander Pfeiffer, who is a Russian mathematician who's been based in Colorado for many years. It's got to be up there as one of the very most wonderful books of all time for communicating an area of mathematics to non-mathematicians or recreational mathematicians. It's just inspiring. And so, I thought, well, okay, I'm definitely going to have a go at this. And I got very, very lucky. I literally found my solution within only a few weeks of starting to try.
Right. There is a similar story about a guy from Warwick. Unfortunately, he's the founder of the Warwick mathematical department, Zeeman. Basically, there is a story about him trying to prove the untiability of a knot in 4 dimensions, which he attempted for 7 years straight. And at some point, he just decided to prove the opposite. Maybe it is untieable. And he succeeded within a few hours. Which brings me to my next question. So it seems like you got this, not really beginner's luck, but you have this outsider's perspective on a problem, because people who grow up as mathematicians end up being in this sort of paradigm of thoughts and expectations. And some people will not even consider a problem because it is customary to believe that it's hard and so on. Do you think that it's a big problem that we have in science in general? And how can people fight that? How can you pretend to be an outsider?
Yeah, well, I think it's different in different sciences. So in biology, I'm not sure it's really possible to pretend to be an outsider if you're not. I think I succeeded and made some important conceptual insights in the few years following my switching fields, basically because I really was an outsider, and I really did come in with a different way of thinking about various problems. And this, of course, is by no means one-off. Like the whole of molecular biology was created in the 1950s by a bunch of physicists, right? These things happen quite often. In mathematics, I'm not, well, of course, I am an outsider in mathematics. I only do it for fun, so I can't really speak to it with the same level of expertise. But my gut feeling is that actually thinking laterally, thinking out of the box, is kind of more, it's more part of what everybody does, or at least everybody to the extent that they can. It's kind of more part of your training to think out of the box than it is in biology, for example. And so I think really I just did what a typical mathematician would do, a professional mathematician. It's just that I got lucky.
Sure. If we discuss your proof in particular, just to be a bit more detailed, so your proof is constructive, and as you just described, it probably takes some ideas from Erdos and another guy who reformulated this chromatic number of a plane problem in terms of graphs. So you start with something simple. It's a hexagonal graph with a one extra point inside. You say something about them. Then you talk about monochromatic triples, root 3 apart. So you build more and more complex graphs, and in the end, you have this one central example of a graph which can't satisfy sort of the coloring that we need. So it seems like it looks like a very linear progress that you make with this proof. And the question is, what was the turning point of the entire proof? Because the steps are trivial, but overall it's hard. So
yes, I very much understand the question. So yeah, it all came down to root 3. Well, okay, I started out from the history of the problem, not mainly the things you just mentioned. I mean, I kind of took as granted, as given the fact that one needed to look for a 5 chromatic unit distance graph. That was it. The question is, how do you find a 5 chromatic unit distance graph? And in Slifer's book, there is a very thorough account of the work done by a brilliant guy named Paul O'Donnell about 25 years ago now, along with his colleague Rob Hadwiger. Neither of them are in mathematics anymore. Well, Hadwiger is still in computer science. But anyway, O'Donnell was interested in finding a 5 chromatic unit distance graph. And his approach was to say, well, okay, let us start by looking at 4 chromatic ones that are not rigid. In other words, where you can flow them, you can move the vertices by incremental amounts while maintaining unit distance. So, like if you think of a square, for example, obviously a square is a two chromatic thing, but you can move the vertices and you can make it into any kind of rhombus, right? Mm-hmm. And similarly, a pentagon is a 3 chromatic graph, which can be unit distance with a whole bunch of shapes. So it turned out to be pretty easy to come up with 4 chromatic unit distance graphs that are not rigid. And O'Donnell played with these things for the entirety of his doctorate, and it didn't work. He did get his doctorate because he was able to show, among other things, that you could make 4 chromatic unit distance graphs of arbitrary girth, so the minimum length of a cycle, right? Which is pretty cool. But at the end of the day, it didn't work. And I came across this, and my intuition was, well, okay, what we're seeing here is that the advantage given by flexibility, which of course comes down, what he was looking for was a case where you could flex the thing into a particular shape where certain vertices were unit distance apart, which didn't need to be, and so you would have additional edges arising from that, right? But the flexibility given by that is that kind of outweighed, it's outrun by the flexibility of coloring, by the fact that the graph is just not very complicated, and therefore there are many, many different four colorings that you have to somehow prohibit with your additional edges. And it just wasn't working. So I thought, well, okay, what would constitute going in the opposite direction? Trying to make a graph that certainly was not in any way flexible, it was completely rigid, but it had so much 4 chromaticity in it that somehow the 4 chromatic subgraphs of it were mutually incompatible. So the overall graph would be 5 chromatic. And that was when I realized that root 3 was a big deal. Because in the motor spindle, which is this famous 7-vertex graph that's for chromatic, you've got 2 pairs of vertices that are exactly root 3 apart. And because of the arrangement, at most one of them can be monochromatic. Obviously, they're not joined by edges because the edges are only of length 1. Mm-hmm. But you can't make both of these root 3 pairs the same color, monochromatic. So, supposing you had a graph that had loads and loads and loads of motor spindle in it as subgraphs, right? Then basically you would expect that it would be difficult to have more than about half of the root 3 distances in that bigger graph be monochromatic. Because you knew that every individual motor spindle could not. So if you have just lots and lots and lots of motor spindle, then they share vertices, of course, interlocking, then maybe somehow, you're going to be able to, it's going to be impossible to go above some certain threshold of how many root 3 distances are actually monochromatic, at least in the middle of the graph where the density of everything is high, right? And then I realized that if you look at hexagons, you mentioned hexagons a moment ago, then you kind of are in a very interesting situation because there are only 4 essentially distinct ways to 4-color this 7-vertex graph, the hexagon with a central vertex. And if you count the number of pairs of vertices that are root 3 apart, there are 6 of them, and if you look at each of the 4 colorings, then the number of those root 3 apart pairs is different for each. It's either 0 or 2 or 4 or 6 of the 6 that are monochromatic. So I said to myself, well, this kind of means that maybe it will be possible to create a graph that's got a lot of motor spindles and also a lot of hexagons, such that maybe one of the hexagons somewhere in the center maybe cannot have 4 or 6 of its root 3 pairs be mono. It's going to have 0 or 2. So it makes things harder. And then I played a little bit with what that would mean, and I noticed pretty quickly that this actually, you could actually make a graph in which that couldn't be true, in which you had a lot of hexagons, it turned out to be 52, right? And at least one of them had to have at least 4 of its root 3 distances be mono, or else you couldn't 4-color the overall thing. That was a fairly straightforward thing. So that's basically 1/2 of the paper I published back in 2018, 1/2 of my instruction. But then I've got the other half to do. I've got to actually find this graph I was talking about a moment ago that has so many motor spindles that you can't color them in that way. Mm-hmm. And that took computation. It didn't take a lot actually. It was easier than I thought. The first graph I found that had that property only had about 1,500 vertices. So if you put 52 of those together, basically in the way that I just mentioned, then you're up to like 20,000 vertices even after you're merging coincident ones. So that's quite a big graph.
But excuse me, people from Polymath 16 have reduced that size down to around 500.
I'm coming to that. So yes, once I found my graph that was 20,000, I said, well, okay, let's try and reduce it. And I got it down to 1,500 and something pretty quickly. So my original paper back in 2018 had a graph that was 1,581, I think it was. That's as far as I took it. And as you say, other people have taken it further. I was very happy that there was a lot of community interest in this. And I had taken part in a very minor way in a polymath project a few years earlier, Polymath 8. Mm-hmm. So I knew the polymath concept and I knew Terry Chow and so on. So I wrote to Terry and said, listen, would you fancy this being a polymath project? And he said, well, maybe. And so we had a little bit of the way he does this, a little bit of a community discussion of like, is this polymath worthy? And it came out very quickly that a lot of people thought it was. So we started Polymath 16 on this. And it's been fantastically successful. In fact, in one sense, it's been by far the most successful polymath project ever, namely in terms of the number of amateurs that it has brought in. Mm-hmm. So most of the results that have come out of the polymath project, in fact, pretty much all of them actually, have been from recreational mathematicians like me.
So it's a playground for people like you.
Totally.
Just to mention the power of collaborative thinking in mathematics, we can also remember what happened to Yitang Zhang when he produced his result about, well, not twin primes, but he gave a finite bound on the distance between primes, which around, so he gave a bound of roughly 50,000, but as soon as he
it was 70 million.
But as soon as it was published, people reduced it down to 600 in no time.
So that was, in fact, the polymath project that I had taken part in earlier, polymath number 8.
Oh, that's the one. I didn't know. Yeah. I didn't know.
It actually was only reduced a very small amount, like down to like 10 million, before polymath 8 was initiated. Everyone said, this is an obvious polymath project. And it started pretty quickly.
Right.
That was very successful, and projects were being made all the time, and I was getting more and more involved, basically because of my computational, I can write software better than the average mathematician, rather than because I had any actual understanding of the math. And it got down to like 4,000 and something, and then a young British mathematician named John Maynard, an extraordinarily brilliant guy, made another big breakthrough. They immediately brought it down to like 700, and then he joined the project, and long and short of it was, it got down to 246, I think it was, before everyone decided we had enough. But my sense at the end of the project is that actually it could have been reduced to maybe 150.
Right. Well, I didn't know that Polymath 8 was about that, so it's good we make that connection. Sure. So you are foreseeing my next question. You couldn't do it without the computer aid, so you outsourced certain combinatorial search to computer, and although your proof doesn't rely on that in any sort of major way, there are people who argue that we might overuse computers in mathematics, and that's bad because it doesn't necessarily give us any insights. Even though you crack this problem, it doesn't, give birth to any new methods of attacking similar problems. And people had that problem with the 4 coloring theorem, if you remember. In the 80s, it was proved almost entirely by a computer, and people were thinking, well, is this mathematics? Is this what we're doing? What is your take on it?
My take is that computer proofs are perfectly valid if one just asks the question in a binary way, is a proof valid or not valid, but that they are unsatisfactory in the sense that they do not give understanding, as you said. They're not giving enough understanding anymore. Therefore, I'm happy with the fact that most mathematicians these days are comfortable accepting a proof that relies on computation, but they still keep looking for one that relied on less computation or no computation. And indeed, that was very much enshrined in the description of the polymath project, polymath 16, at the beginning, that one of the goals was to use fewer vertices, but one of the big goals was to reduce the amount of computational requirement. And that was the big goal where we succeeded. One of the other recreational mathematicians, a brilliant Russian guy in the young parts, came up with a human proof. It's a very laborious human proof. It would take you a week if you actually did it on pen and paper, maybe 2 weeks, but it definitely can be done without computers. Essentially, it's a brilliant idea that starts from a 13-vertex graph, which is essentially a slightly expanded version of the Golem graph. So this is a well-known 4-chromatic graph.
Yeah, it has a hexagon and a sort of twisted triangle inside with extra...
Yeah, so the version that he used was one which has 2 of those triangles in the middle.
Okay. What's the angle they make? Do you remember?
That's right. So you've got a kind of an outer hexagon and an inner hexagon. The outer hexagon is actually joined up, and the inner hexagon consists of 2 triangles.
All right.
So, anyway, so he simply enumerated the 4 colorings of this thing, right? And he was interested specifically in the 4 colorings in which there is a monochromatic triangle in the outer in the original hexagon, the outer one, right? And from there, he was able to notice that whichever of the colorings you look at, the four colorings, you can add a vertex that's not yet there, but which is unit distance away from existing vertices of at least three other colors. Right?
Okay.
If you can do that, if you've got a coloring of the 13 things, you find a point which is not yet a vertex, but it's unit distance from points that you have colored in three different ways, right? Then that new point that you could add, its color would be forced, subject to the coloring of the original one, right? And he found that you could always do that. And in fact, that you could always do it successively. So he was able to show that you could build a 5-chromatic graph just by that, just by putting forced ones in. Actually, well, you had a couple of subcases here and there, but it wasn't completely that simple, but it was very nearly that. And yeah, I mean, to my mind, that was definitely the foremost achievement of many, many achievements in the polymath project, the finding of that human proof.
Sure. So you're still up for people producing sort of more human intuitive ways of proving the same thing.
Well, intuitive might not be the right word, because this process of creating this graph by hand without a computer is still very mechanical, and you don't really know why you're doing what you're doing.
Okay.
So I think that's kind of a separate thing. Sometimes you get a better understanding of why something is true from a human proof, but sometimes, even if it's a human proof, you still don't understand why it works. So it's kind of more to it than that.
So just to conclude on Hadwiger Nelson, the chromatic number of a plane is now down to 5, 6, or 7. What do you think it will take next sort of mathematicians to narrow that range even further and potentially have an answer? Can we use the same methods, or is it qualitatively new approach that we need?
Yeah, it's a great question. So in order to get it up to 6, in order to show that it's not 5, one would need to find a 6-chromatic unit distance graph in the plane. And I guess if you ask me my intuition on this, I think we'll do it, but I think it's going to be really hard. So I often say, I think we will do it before I die, but of course, given my day job, that's a kind of weak statement, right? It's going to be really hard. I would not be at all surprised if it turns out that such graphs exist, but that the smallest ones have more than 1 million vertices. Mm-hmm. And exactly how we would find them is probably going to take a bunch of new insights. Kind of the same thing that I did. Just saying there's this weird thing about root 3. But doing it in with a lot more computational help than what I needed. Finding a graph that's only 500 or 1,500 or even 20,000 vertices is nothing compared. Mm-hmm. So that's what I think. In terms of whether it's 6 or 7, though, that's a much more interesting question. So I really, I wouldn't bet my house on either 6 or 7. I would bet my house that it's not 5, but not on whether it's on between 6 or 7, because we're so close to getting a 6-chromatic covering of the plane. You can create a tiling of the plane, a simple tiling, in which the ratio of the diameter of a tile to the distance between same-colored tiles is 0.992.
Right.
Right. So really, really close to 1. Right. And and that's without even getting particularly clever about the tiling. Mm-hmm. One thing that has been established pretty clearly, not formally, but pretty clearly, is that you can prove a lot of things about tilings that you can't prove about specklings. In other words, colorings in which some of the regions have measure 0.
Yeah.
Just like dots or lines rather than areas. Right? And even worse than that, even if you do restrict yourself to tilings, you can have what I like to call Siamese tiling, in which it's not necessarily the case that every pair of tiles is at least 1 unit apart. Sometimes you can have two small tiles, that are closer than that, right? So they're furthest, you understand what I'm saying, right? And it turns out to be much, much harder to prove stuff about those, right? I think it gets worse. For example, with unscalable tiling. So we do know that you need 7 colors if the coloring is a tiling and it's block structured. In other words, it doesn't have these Siamese things I just described. And also, one third thing, every pair of points is not just infinitesimally more than one apart if they're the same, but it's strictly more than one. So the inequality is strict. If you say all that, then it would prove more than 20 years ago that you needed 7 colors. But it turned out there are quite interesting colorings where it's not strict, where I call them unscalable tiling, in which basically some of the boundaries between tiles are arcs of radius 1, so that you can have that tile has a neighboring tile of a particular color, and it also has another neighboring tile of the same color, but only meeting it at a vertex. And the arc is, of course, centered on that vertex. Those tilings turn out to be really interesting. And there's very, very tantalizing reasons to believe that you can do better with those. For example, it turns out if you try to tile the surface of a sphere, of a sphere that's larger than about 6, I think the radius has to be at some number anyway. Then if you restrict yourself to scalable tilings, in which you don't have this, what I just described, then you need at least 8 colors. That was proven by a brilliant graduate student named Philippe Agostin about 2 or 3 years ago. But if you do allow these unscalable tilings, then you can do it with 7. That was proven by one of the other recreational amateurs in the Polymath project. So yeah, so there's definite, there's a huge amount to play with in this whole area. So I would absolutely not put money on either 6 or 7.
Right. That gives a lot of attack vectors for us to consider. In terms of that, what is your next project, and are you looking for collaborators this time?
So I tend to look for collaborators when I really understand what the thing is. And actually, right now, I do have something along those lines. And I just found a really great collaborator.
Right.
Literally a couple of weeks ago. So the thing I'm working on is the perfect cuboid conjecture, which is, of course, even older than the Hadwiger Nelson question. The idea, the question of whether you can have a cuboid, all of whose edges and face diagonals and main diagonal are integers. So most people know what an Euler brick is. It is a cuboid in which the edges are integers and the face diagonals are integers. So essentially what you're saying is that each face is Pythagorean, right? But there's no requirement for the main diagonal to be an integer as well.
So just to make it more accessible to the audience, we have like a box with straight faces. We want all edges, all of those diagonals, and also the internal diagonals to be Euclidean, to be Pythagorean. So they want
to be integers, right? So a triangle is Pythagorean if it's a right-angled triangle and all 3 of its edges are integers.
Exactly. Yeah.
Right. And so a rectangle is Pythagorean similarly if its edges and its diagonal are all integers.
Sure.
Right. So an Euler brick is a cuboid, a box, just like you described, in which all of its faces are Pythagorean rectangle. Mm-hmm. In other words, all of its face diagonals are integers as well as its edges. And then finally, a perfect cuboid is an Euler brick, which in addition has an integer length for its main diagonal between opposite corners. Okay. All right. So 400 years ago, someone found an Euler brick. It turns out that the edges have lengths 44 and 117 and 240. And about 380 years ago, someone came up with a formula with just 2 parameters for describing an infinite family of these things. It turns out, however, that it's easy to show that no member of that infinite family can be perfect. It never has an integer length for its main diagonal, right?
Is it possible to have the main diagonal an integer but something else failing? Is that?
Yes, it is. People have looked at that. Yep, people have looked at that.
Okay.
And that's also pretty easy to do. But getting all 7 lengths, all 3 edges and all 3 face diagonals and the middle and the main diagonal, that no one's been able to do that, but also nobody's been able to show that it's impossible.
Mm-hmm.
And a lot of the problem comes down to the fact that it's a needle in a haystack. It's just too easy to find Euler bricks, or for that matter, the version of the Euler bricks that you just mentioned. And so you just, you can compute these things, but they're sporadic. As I mentioned, there's this one family which has been excluded. Other than that, you just have to look. You say, okay, is this another brick? Is that another brick? And then you ask, is it also a perfect cuboid? And it never is. And so computationally, it's just, just search and search and search and never find anything, which is very boring. So of course, the hope is that we would find a way to narrow the search, to do a more efficient computer search. And I made an observation not long ago, a few months ago, which does exactly that. Essentially, it transforms the problem into a 2-dimensional problem, which is all about Pythagorean triangles. Mm-hmm. So it was discovered way, way back, like in the time of Pythagoras, that all Pythagorean triangles can be parameterized using just 2 parameters, well, subject to scaling, where you say, okay, well, if you take any 2 numbers, P and Q, right, and you say, okay, we're going to make one of our edges of our triangle be 2 times P times Q, and the other edge, the other perpendicular edge is going to be P squared minus Q squared, then the hypotenuse is going to be P squared plus Q squared. And it turns out that this is bidirectional. It's not just that for any P and Q, you get a Pythagorean triangle. You can also prove quite easily that every Pythagorean triangle
is of that form.
Is obtained in this way, that's right. So the thing I noticed was with regard to Pythagorean triangles that have that share an edge. So if you think about it, because one of the legs, one of the non-hypotenuse edges of the triangle is 2 times P times Q, right? Then if you pick a number that just has a lot of factors, right, then you can chop it up into 2 times P times Q for an awful lot of different choices of P and Q, right? And of course, every different choice that you make for P and Q will give a different value for P squared minus Q squared, the perpendicular edge. Mm-hmm. Right? So you'll get a different shape of triangle, right?
Yeah.
Fine so far. That means, like, obviously, the larger a number you look at, as you go up, you get numbers with more and more factors than any number had before, any smaller number had. You can find numbers with arbitrarily many factors, and therefore with arbitrarily many shapes of, so let's call them Pythagorean partners, okay? Values for P squared minus Q squared for a given 2PQ, right? Now, it turns out that the perfect cuboid question can be transformed into a question about those. All you need to look for is numbers that have 3 Pythagorean partners in geometric progression. So you've got a number, and it's got a lot of factors. You're going to call it 2PQ, all right?
But PQ are not necessarily prime. You just decompose them into 3 factors, but PQ are not necessarily.
Yeah, well, P and Q are not necessarily prime, but they have to be co-prime.
Co-prime.
They must not have a common factor.
Yeah.
Okay? So, because we're only interested in the shapes of the triangle, we can totally scale things as much as we like. We can multiply by a lowest common multiple or whatever, all right? Mm-hmm. So don't worry about that. We just worry about the shapes. So the question is, can we find a number which we can decompose in 3 different ways into 2PQ, right? Such that if you calculate the corresponding P squared minus Q squared for each of the 3 choices of P and Q, then you have a geometric progression. So why is this important? Why is it interesting? It's interesting because there turn out to be examples of this, but very, very, very few. In order for this to translate into a perfect cuboid, you need one more thing to be true, which is to do with basically the difference between the square of two of the members of the geometric progression. Don't worry about that. The point is that it's not so bad an example of looking for a needle in a haystack as it has been historically. It's still looking for a needle in a haystack, but it's a much smaller haystack. Okay?
Compared to countable infinity, it's still...
Well, no, I mean, the point is you can search up to a much larger number, like number of digits in the numbers you're looking at, than you would be able to otherwise. So it makes it a much more efficient search. It's still a computer search, it's still a blind search, but it's a much more efficient one. And what makes it even more interesting is that with the computational resources at my disposal, which are pretty modest, it looks like the number of hits that you get, the number of numbers that you have this, geometric progression of 3 Pythagorean partners, is tapering off. That it seems to be hitting a maximum around 15 digits long, around 10 to the power 15. But I'm not completely sure because I can't get very much further than that with my computational resources. So I just did what a celebrity does. I've got 50,000 Twitter followers. Most of them are interested in aging, but some of them have other stuff going on. So I just put out a tweet and I said, right, I have this new approach to the perfect cuboid conjecture. If you are interested in that and you also have serious computer power at your disposal, please email me. And somebody did. So I now am working with this guy, and with a bit of luck, we'll be able to go up to 10 to the power 25 or 30, rather than only 10 to the power 15 or 18, which is what I've been able to do so far. And we will have, at very worst, we will have an answer to the question, is it tapering off? Is it looking like there's a finite number of numbers that actually satisfy this criterion of having 3 Pythagorean partners in geometric progression? If it is tapering off, then it starts to become a question of, can we prove that we've actually enumerated all of them? Because that sometimes happens, right? Mm-hmm. You can actually say there's genuinely this finite number of solutions. Woodell's theorem comes into this a lot in algebraic geometry. And of course, then there's the other possibility that we may see where it's not really tapering off, but we may actually, the more data we get, the more examples, hits we get, the better chance we have of seeing patterns, so that we can actually construct infinite series and then, maybe get from there to an actual perfect cuboid, even if it was computationally way out of sight. And then the third possibility, of course, is the ultimate plan A, where we actually get a hit with the computer set. So yeah, that's what I'm doing now.
Great. I guess it might attract somebody else's attention, so
totally.
People may...
I've been able to talk about it today.
Sure. Well, it sounds great. You're you keep going with...
Anyone who's listening, if you want to get in touch and talk about this and maybe get involved, then, I'm easy to find on Twitter.
Twitter is the best way.
The quickest first way, yeah.
So, I hope people will either know you already or will take their time to familiarize themselves with your longevity work, because you've given, a number of speeches. I think by your own account, you gave around 1,000 interviews over the past 10 years.
Well, I would say I would say certainly over the past 20 years, it's got to be at least 1,000 if we add interviews and talks together, and probably 100 of them are on YouTube.
So you said a lot about your program and about your views, but I had a question which comes sort of around that, because you are a proponent of a biological longevity. You understand those processes, those damages, as you call them, and you think that if we understand that it's possible, we can sort of fight them and finally achieve the goal of a much longer or potentially immortal existence. However, I think as a computer scientist, you must have thought of this. Why can't we think about brain longevity? Why can't we simply concentrate on making our consciousness last forever? Because some people regard our bodies as this unnecessary accessory to the brain, which gets old and in the end kills us. So, as a computer scientist, do you think that it's an interesting question, or you value the biological life as itself?
So, okay, so this actually breaks down into multiple questions. First of all, we have to ask, is the body the appendage and the brain the main thing? Probably it is, but the brain is made of more or less the same kind of stuff as the rest of the body. So the brain gets old intrinsically. We can't just keep things going by giving the brain a new body or an artificial body or anything like that. The brain itself will intrinsically get old anyway. So the only way that we could actually do, in a strong sense, the thing you're describing, is by transferring the actual function of the brain, the personality and consciousness and everything, to different hardware that didn't have the same problem of being squishy and getting old that we have. And that's usually called uploading.
Yeah.
Now, I don't really have all that much of a problem with uploading. I think it's it's ethically, and metaphysically, I can't see anything particularly wrong with it. The thing is that we haven't the faintest idea how to do it at all. We know much less than we would like to know about how to do things the boring, wet way, the things that I'm focusing on, right? Of repairing the damage everywhere. But we know nothing about how to transfer consciousness to a different type of hardware. We can imagine that we could potentially do it without understanding it. And the way we would do that would probably by doing it somehow incrementally. So creating some kind of very, very high bandwidth brain-computer interface that would somehow create a replica of the brain, not just a snapshot, but a running replica, by essentially mimicking what it is seeing the real brain doing. However, then you haven't actually done what you wanted to do. You've created a new person, a new consciousness. Well, whether it's conscious or not is more of a philosophical question, but you've created a new thing that behaves as though it's conscious, but you've still got the old one, and you still care about the old one, so that's a big problem. People try to get around that by saying, well, okay, maybe we can do it in situ. Maybe we can somehow, replace neurons or small chunks of the brain one at a time, and get the replacement stuff to kind of integrate itself into the cognitive network, essentially to learn from the pre-existing stuff around it, right? And then we can replace a new one, and the stuff that we put in the last time will be part of the teacher rather than part of the student, if you like.
Okay.
And eventually we can do it for the whole brain. So that's kind of, the fact that it's incremental is critical, really. It means that at no point do we have two people. We only have one person at any one point. Fine, but then we have to ask, a bit more about how we would do that. Of course, the idea here is if you were to do that, then the things you were putting in would not be wet and squishy; they would be silicon-based, right? But then we have to ask, is it necessary that we should do it inside the skull or not? Yeah, so you get the idea. There's a lot of questions here, and so you ask the questions based on my background as a computer scientist. One doesn't really need to have that kind of background. One just needs to be comfortable with thinking about arbitrarily dramatic eventual technological progress of any kind. That's really what transhumanism is all about. And I don't like to be called a transhumanist, but that's really just because the word is
spoiled.
It scares me. The actual nature of transhumanism is simply having a good sense of proportion about the pros and cons of future technology, really, and seeing that technology tends to be good for you in the end. So yeah, that's my essential feeling about all of this. I think at the moment, the boring, wet approach of just doing medicine and repairing molecular and cellular damage all over, including the brain, is not only philosophically the least challenging and problematic. It's also technically the least challenging. It's really hard, but the other stuff is even harder.
It's a tradition amongst many senior academics to have a list or an undefined list of problems that they like giving to their potential students or potential collaborators to check their savviness, to check their just to see how they think. Do you have any of those problems that our viewers can play around with and just understand how to get into the de Grey club?
Well, that's a tricky one. I think probably the best I can do there is to talk about my introduction to combinatorics and graph theory when I was in my 20s.
Right.
So as I said, I had a bunch of friends who were actual maths undergrads, and PhD students by that time, where they had done computer science. But there was a professor at Cambridge, I think he still is, originally Hungarian, his name's Bela
Bolabash, yeah.
Yeah, well-known guy, fantastic personality, and had a long succession of really talented students who did really well. And a large part of why everybody loved him was because he would do pretty much what you just said. He would challenge his best students with really hard problems that he wasn't really expecting any of them, or many of them anyway, to solve. And there was one particularly famous one, which was a graph theory problem posed in probably 1950, something like that. And it was solved fairly quickly, but it was hard enough that, the solution was an actual publication. It wasn't trivial, right? It was the problem of, can one construct a triangle-free graph of arbitrary chromatic number? So
with what chromatic number?
Of arbitrary chromatic number.
Oh, arbitrary.
This has nothing to do with unit distance, right? You can draw the graph any way you like.
Okay.
It's just like, can you construct a graph that has no cycles of length 3, no triangles, but its chromatic number is arbitrarily high, right? And of course, the way you would do it would be you would try to find one that had chromatic number n and construct from it one that had chromatic number n plus 1, right? And virtually nobody was ever able to solve this problem. And the people who did, it took them weeks and weeks and weeks. And I figured it out in an hour and a half in the back of a bus, just in my head without a piece of paper. I just, again, I kind of just got lucky. But the point is, it really impressed people. And of course, it also impressed me. It was the thing that told me that I was actually fairly good at doing the right kind of visualization to be able to look at questions like this. And certainly, some of the other minor...
is the answer yes or no, by the way? Or do you want to leave it as...
You can do it, yeah.
Okay.
You can create such graphs. That's what I don't do proofs very well. I do constructions, right? That's what I do. So yeah, in the Polymath 16 project, there's been lots of other little kind of, variations on the theme, like how can you do it on the surface of a sphere? I mentioned that earlier, or like how wide an infinite strip can you make that is colorable with only 5 colors? Or how large a disk can you make that's colorable with only 4 colors? Things like that, right? And I was able to solve a few of these things just in my head, to improve on previous solutions. So, that's basically where I seem to fit into the mathematical hierarchy, the mathematical ecosystem. I just have good visualization skill.
I guess what I was trying to say, if, for example, you're about to collaborate with somebody, either in biology or mathematics, there could be some sort of, tests, little problems that are they're very individual, that you can ask them, and it's those questions which you can't Google, they are creative. So would you like to keep them as a secret for people not to be biased when you meet them, or do you have any little problems you can give us so we have a little bit of a thought-provoking aftermath?
In biology, it's completely impossible because biology is a data-driven subject. you need to just know an awful lot of facts
Just
in order
know.
to be able to have interesting ideas or to understand how to evaluate other people's ideas. So in biology, basically, no. That's why I chose to retreat back to the mathematics topic in order to answer your question the first time.
Sure, sure. Well, thank you. It was a very joyful conversation.